Crystals are usually represented by repetition of basic unit of structures called motifs in a defined lattice. For instance, this motif consisting of zinc and oxygen atom can be repeated in any directions to represent a crystal structure. However, a perfect lattice is an idealization because there is always imperfections due to external factors such as temperature, pressure, chemical composition, and so on during experimentation. Imperfections will appear as defects such as vacancy, interstitials, and substitutions, to name a few. These will affect the electronic, structural, optical, and mechanical properties of the material. For instance, an electron is excited to the conduction band in the presence of an external sources. It will relax and it will go back to its ground state, thereby producing a light whose energy is equal to the band gap. With defects, there will be a defect level, and the electrons can be relaxed to the valence band, or it could relax into the defect level, producing a different wavelength of light, which can be observed using photoluminescence measurements. Wurtzite zinc oxide is an ionic semiconductor with a band gap of 3.37 eV. However, zinc oxide has a lot of voids, hence it is susceptible to defects. Iron is a candidate for defect because it has relatively the same ionic radius as zinc. Hence, the main goal of this study is to understand the physics of formation of iron-related defects using first principles calculations. First principle calculations enable us to predict the material properties without doing experimentation and use it to optimize the appropriate parameters used in the experiment. Commonly used methods is the density functional theory. DFT transforms the many-body Schrödinger equation into a quantum equation of single independent electron systems. The software we use is the Vienna ab initio simulation package using the commonly used pseudopotentials and exchange correlation functional. Defects include substitutionals, interstitials, and complex defects. Results include the projected band structure, density of states, crystal structure, and charge density difference.